In today's video, we're going to be talking about the second derivative test. If you haven't seen the video on the first derivative test, go watch that first. I'll link it up here in the corner. The second derivative test gives us additional information about the graph that the first derivative test didn't give us. In the first derivative test, we could figure out where a function is increasing and decreasing, we could find critical points, but we couldn't find inflection points or concave up and downness, which we'll talk about in this video. First of all, some quick review. Let's say we had an f of x such as x squared. The first derivative, f prime of x, would equal 2x by the power rule. The second derivative, or f double prime of x, would then just be 2. Essentially, you just take the derivative again. It's just another step. And we're going to use the second derivative to find out more information about the graph, and using information from the first derivative test along with information from the second derivative test, we'll be able to graph our functions. So let's talk about some of the stuff that I was talking about just a second ago. So I've written two rules down about the second derivative test. If f double prime of x is positive on the interval from a to b, then the graph is concave up on that interval. And if f double prime of x is negative on a to b, then the graph is concave down on a to b. Now you may be wondering, what do I mean by concave up and down? Well, let's draw a graph to make this a little easier to understand. Here's our xy plane, and we'll use blue to draw the graph, because why not? I haven't used it much in a while. Let's say we have a graph that looks something like this. I don't have a numerical function to go along with this, but it'll show us what I'm talking about. Here's one way to remember it. If this little curve could hold water, then it's concave up. If the water spills out on either side, then the curve is concave down, like on this side. Another important thing to know is what I've written down over here. If f double prime of x is greater than 0, then f prime is increasing. In other words, the graph is increasing at that point. If f double prime of x is less than 0, then f prime is decreasing. And I want to highlight this point roughly there. This point is an inflection point. The inflection point on a graph is when the graph changes concavity from either concave down to concave up or concave up to concave down. These points will be very important when we graph these functions because we need to know where the concavity changes. We'll talk more about the inflection point when we get to graphing. We're not there just yet. So let's talk about the second derivative test itself. The second derivative test states that c is a critical point. And if f prime of c, aka you plug in c to your function, is less than 0, c is a relative maximum. So it's the top of a curve, kind of like this little graph here. If f double prime of c is less than 0, c is a relative minimum, aka the bottom of a curve. Kind of like this, kind of like just x squared. And if f double prime of c equals 0, the test fails. And we're about to start graphing, so in this top right corner, I decided to draw a little diagram that can help you visualize everything better. If your graph looks something like this, it's concave up, it could hold water, but the function is also increasing. Similarly, this function is also increasing, but is concave down. It would spill water. Here, the function is concave up, but it's decreasing. The function's getting smaller and smaller as we move to the right. And same thing over here. This function is concave down because it would not hold water, and it's also decreasing. This will come in handy when we start graphing in just a second here. In fact, we're going to do one example for this video, and this example is actually the same one I just used in my first derivative test video, so there will be some points that I skip over. So like I said earlier, if you don't know the first derivative test, go watch that first, and we'll come back to this video. So like I was saying, we're going to use the same example we used last time, which was x cubed minus 3x squared minus 9x plus 1. And we're going to use this function in order to find where the function is concave up, concave down. Remember, refer to this graph if you get stuck. We're going to figure out the inflection points, marked as IP, and then we're going to actually graph this function because using the second derivative test and combining that with the first derivative test, we can actually graph the function and get it pretty correct. So first of all, we should probably find both of these derivatives. F prime of x, which we found last time in last video, is equal to 3x squared minus 6x minus 9. The derivative of a constant is equal to 0, so we don't have to write that. But we also need f double prime of x, aka the second derivative. So what's the derivative of this function? Well, we just do the derivative again. This is equal to 6x minus 6. And then once again, a constant just turns into 0 when you take its derivative. So this is our second derivative. And in order to find the inflection points, we need to make this equal to 0. Just like in the first derivative test, we need to set the first derivative to 0 to find the critical points. By the way, the critical points of this function, which are right up here, labeled as CR, are equal to -1 and 3. We'll use these later, and in my last video I showed you how to find these in more detail. So like I said, go watch that if you haven't already. So first, let's add 6 to both sides, like so. So 6x is now equal to 6. Divide by 6 on both sides, and we get that x equals 1. This is our inflection points right here. Now, just like in the first derivative test, we're going to build out a sign chart. And, well, we only have one point that we need to check, so we're just going to mark 1 right here. What we're going to do is we're going to plug in numbers that are less than 1 to figure out what's going on the left side, or left of our inflection point, and then plug in a number bigger than 1 to figure out what's going on the right side of our point. And since we only have 1 point, we only need to check one number on this side and one number on that side. Nice and easy. So first, let's try f oh wow, f double prime of 0 equal to, which would then be equal to x just being 0, 6 times 0 minus 6, which of course equals negative 6. This number is negative, therefore this side is negative over here. F double prime of, let's just choose a number higher than 1, say 2, is equal to 6 times 2 minus 6, which is equal to 6. That's a positive number, therefore on this side we are positive. And you know what? I'm going to make those signs a little bit clearer. We're going to put a red plus sign here and a red negative sign here. There we go. I hope that's a little easier to see. So with just this sign chart, we can actually answer part A. Where is this function concave up and concave down? Well, wherever the function is negative, the problem is concave down. So we're going to answer A over here. It's probably going to get blocked while I'm teaching, but I'm going to write it over here. This function is concave down from negative infinity. Remember, we don't include infinity because it's not really a number, to negative 1. And we don't include negative 1 either because at negative 1 we have an inflection point. So we can't actually include it as concave up or concave down. This function is concave up at 1 to infinity. And once again, we cannot include either one of those. So that's part A answered. Let's move on to part B. What are the inflection points? Well, we already know our inflection point just based on our sign chart. So B, the inflection point is equal to 1. We only have 1 in this function. So that's nice and easy. Now part C is going to be the hardest part. We're going to use all this room over here to graph. So I'm going to write C over here, and we're going to graph this function out. Let's draw a little XY plane in order to do the graphing. And you know what? Let's use green. I haven't used green much recently. That should be a good color for this graphing. So we're going to mark the important points. First of all, we have our critical points at negative 1 and 3. So here on the graph, I'm going to mark negative 1. We're going to mark 3 over here. And the other point that we're interested in is positive 1 because that's an inflection point. So here's positive 1. So now that we've marked all of our points of interest, let's talk about some of the values that we already know. First of all, from the first derivative test, we know where this function is increasing and decreasing. In my last video, I talked about that in more detail, but for now, I'm just going to write it down so we can do this graph. So I'm going to write all the relevant information here. Increasing. So this function is increasing from negative infinity to negative 1. Union, that's what that is union. So we have a gap in between here, but we have two different areas where it's increasing. So we union them or put them together. And then this function is increasing from 3 to infinity, right there. This function is decreasing. By the way, decreasing is labeled DECR and increasing is labeled INCR. This function is only decreasing from one area, from 1 to 3. This function is concave up or CU. I don't know if I mentioned that, but concave up is CU. It's just a shorter label. This function is concave up from 1 to infinity, aka forever after point 1, and then concave down from negative infinity all the way up to 1, because that's where our inflection point is. So then it flips to concave up after that. And something else we know based on our critical points, which I labeled up here and on the graph, is that at the critical points, there is a relative maximum and a relative minimum. So what we're going to do is we can plug in negative 1 and 3 to figure out exactly what point is our relative maximum and what point is our relative minimum. I'll save you the trouble. At negative 1, y is equal to 6. And at 3, this function is equal to negative 26. So this is not to scale because I do not want to draw this to scale because it would not fit on my board. So basically, if you wanted to figure out these points for yourself, you could just plug in whatever these critical points are to your original function f of x, and that would give you your relative maximums and minimums. And remember, we know that this is a relative maximum and this is a relative minimum because we know at the top of a concave down curve is a relative maximum, and at the bottom of a concave up curve is a relative minimum. So we have all the information we need. First of all, we are decreasing down here, and then it goes up and up and up and up and up, and it hits negative 1, 6. And we know that this is a relative maximum. So then the function starts to decrease from here, and at 1 is the inflection point. So it starts to go down. I just went directly through the number 1, but I'll redraw it. And then it reaches this relative minimum here at 3, negative 26. And then at 3, it continues to go upward. So our function looks something like that. And this is a pretty good rough estimate considering we don't have calculators to use for these problems. And, well, we're just doing it by hand. And using just the second derivative test combined with the first derivative test, we can graph just about any function. So just to review, part A, we wanted to find where the function is concave up and down. We know that this function is concave down from negative infinity to negative 1, as you can see here, and that it is concave up from 1 to infinity, as you can see here. We know the inflection point is 1 because at 1 is when this concavity flips from concave down to concave up. And based on the first derivative test, we know our critical points were negative 1 and 3, labeled on the graph. Like I said, if you want to learn more in detail about critical points, go watch the first derivative test video. And knowing where our critical points are helps us figure out what our relative maximums and minimums are just by plugging it into the original function. So, and C is just the graph. That's all we had to answer here. There's no other numbers here, don't worry. I hope you guys enjoyed this video. If you did, consider subscribing, and if you need more lessons, check out the Calculus 1 playlist linked here, especially if you need that first derivative test video. I'll see you guys in the next video.